Imagine this, you're driving a long road trip to God knows where, and you know you're going to be driving this road for ages, so you press cruise control. You take your foot off the gas, your car stays going the same speed. How does the car know how much throttle to apply to maintain whatever set speed? It does this through PID controllers, or PID controllers. What are those? The PID controllers are used everywhere from your thermostat to your oven. They're commonly used in automation as well as everyday use to reliably maintain a system's output, whether temperature, pressure, motor speed, position, really just anything that can be measured with a sensor. How does it work? To understand, we gotta break down what PID stands for. P stands for proportion, I stands for integral, and D stands for derivative, each term responding to a different aspect of error. P responds to current error. The larger the error between the process variable and the set point, the larger the output response. If I'm running somewhere and I'm currently very far from my destination, I'm going to run very fast to get there. I accounts for past error. If I'm running somewhere and in the past I've been continuously far off from my destination, I'm going to run a little further or a little less depending on if I'm overshooting or undershooting my target. D anticipates future error based on the rate of change of error, aka if I'm running somewhere and I'm getting closer to my destination, I should start slowing down so I don't run past it. Now that we have a basic understanding, here's a more visual understanding of the math behind it. The difference between these two lines, the set point and the processing variable, is the current error, which P responds to. The area between these two lines is the sum of error over time, which I responds to. Plotting the current error and taking the slope of that line gives us the rate of change of error over time, which D responds to. This thing is a whole lot of calculus. Fun fact, love calculus so much, my friends and I wore calculus shirts to our Calc AP exam. That's me, and that's the face of my calculus teacher, Mr. Collins. Continuing with the graph, once the system settles, that's the steady state error. Why don't we try implementing our own PID controller? Here's our system, this robot. Or actually this robot. We want to control where the robot turns. Our sensor will be the robot's internal IMU. We're going to have to tune its KP, KI, and KD values. To do this, we start everything out as 0, and then we increase proportional until we see oscillation in the system. Then we increase KI until we reach minimal steady state error. Finally, we increase KD to decrease overshoot. And you're done. Let's see this in action. Now we have a robot that turns to whatever position we give it. Thanks for watching, and I hope you learned something. Here's my works cited. Bye!